My name is Robert Wille. I'm with the Johannes Kepler University Linz and the Software Competence Center in Hagenberg, both in Austria. And I welcome you to this panel on quantum computing at this year's Design Automation Conference. Unfortunately, a panel which is only virtual and which is pre-recorded, but still we hope that we can provide you with an interesting 1 hour, 1.5 hours in which we talk about this very exciting emerging technology. And we've got 3 very great distinguished panelists for today's chat. And those are Christa Swarf from Microsoft Research, Austin Fowler from Google, and Leon Stark from IBM. And I don't introduce them because they can introduce themselves much better. And I would like to ask, first of all of you to briefly introduce yourself for this panel. Christa, maybe you can start. Who are you and what you're working on?
Happy to. Well, thank you again for the invitation to be a part of this wonderful panel. I'm Christa Savory, and I'm a quantum computer scientist. My day job is leading and managing the quantum software and systems engineering group at Microsoft, where we are focused on bringing forward end-to-end capabilities for quantum acceleration, going from the quantum algorithms all the way down to the metal. We produce and work on developing that software stack, including the applications, quantum algorithms, all of the algorithmic functions you need across that stack. And we also work on Azure Quantum, which is a public cloud service on Azure.
Terrific. And I'm pretty sure we're going to learn more about that in a moment. But let's quickly introduce also our next panelist, which is Austin Fowler from Google. Austin, can you introduce yourself? Who are you and what you're working on?
Yeah, so very similar to Christa. I work on the software side of building a quantum computer. My specific area of research is on surface codes and decoding them in real time with very low logical error rates. So my primary responsibility is to deliver a hardware and software system that can keep pace with the quantum computer and decode it in real time.
Terrific. And last but certainly not least, we've got Leon Stark from IBM. Leon, who are you and what you're working on?
Yeah, thank you, Robert. And first, thank you for inviting me to the panel. I'm probably the one that doesn't have a day job in quantum, but I run our EDA organization. But I'm very closely affiliated with our quantum team, right, for mainly 2 reasons. Is one, we have built quite a few systems that are kind of out there. So we try to provide some of the EDA tools that help them optimize and just build better quantum hardware, doing some of the simulations, doing some of the design on both the control stack as well as the quantum chips themselves. And secondly, as an EDA algorithm developer, I'm very curious, like, hey, when can I use a quantum computer and do something that actually works better than on my conventional computer? So I'm kind of curious and interested in quantum algorithms and some of the key optimizations and areas that are being explored that, also underline many of the EDA algorithms that hopefully we can, sooner than later run on the quantum computer.
Perfect. So this is our panel. Many thanks again for making the time. And for our audience here, you don't have to be a quantum physicist in order to be able to follow these discussions. We're actually trying to make this panel a panel for design automation experts. And obviously, quantum computing is having a momentum right now, and we want to provide you with a rough overview of what our 3 panelists think about the development and how design automation in particular can help in this development. But to get a little bit an overview, get a little bit context, let's start with the first segment in this panel. Let's talk about quantum computing in general. What is this all about? And particularly, let me start with a general question to you, Christa. Quantum computing is around for decades, actually. The roots go back to the last century, of course, and it has been investigated for a very long time. But particularly in the last years, we really have seen this momentum. Industry is sort of getting on board after, as said, almost a decade, almost a century, where just this topic has been considered by researchers. So what do you think is the main reason why this whole thing gets this momentum right now, and why we're seeing this? Why would you seeing this momentum now and not why haven't we seen that 10 years ago? Why now?
I think we're at such a special point in time, right, where we're seeing advances across the hardware and the software, coming together and showing that there is true promise to quantum acceleration, right? There's really, with a quantum computer, I think first, we recognize that classically we're hitting limits, right? In terms of what we can compute, the areas we can compute. We need some revolutionary advances to unlock the capability to have new types of solutions, right, for very hard problems. So let's think about some examples. I think when we think about the impacts of quantum computing on our society, one of the biggest is really around the ability to predict the outcome of chemical processes, right? This is very hard classically for a large variety of molecules and materials. We want to be able to produce chemicals, materials, right? Other things actually have predictive design for chemistry and materials. Now, even if quantum computers only solve this area, this will remake the global economy. And so I think part of that increased investment right now is the promise to produce a machine, right? A capability, this whole set of technologies. It's a bunch of components that have to come together into a scaled system that will unlock the ability to have more predictive design for chemistry and materials. Now, the types of problems that we're talking about, it's everything from helping improve the way we have, the way we do combustion, right? Let's boost fuel efficiency. Let's help perform combustion where we don't have as many pollutants going into the air, less toxic gas entering the air. Let's look at clean energy, improve carbon fixation, have better solar energy conversion, better materials to do that. In clean water, we could find better catalysts, right, that help actually kill that bacteria, remove contaminants from water. And then across, energy efficiency, we might look at finding a higher temperature superconductor that could help with better or, even lossless power transmission. These capabilities are unlocked with quantum computing. The key is that quantum computer has to be scaled up to more than 1 million qubits. And so I think right now you're seeing so much investment as well. It's not only the promise of the application, but we actually need to engineer, develop, and build a system that gets us to that type of scale to see these promises unlocked and these solutions unlocked.
So according to you, it's the applications and the needs and maybe also the limits of conventional computing. At the same time, maybe with the prospect that we maybe reach these millions of qubits in the near future. Leon, would you agree, or do you see different or other reasons why quantum computing is getting momentum right now?
No, I think let me complement this a little bit, correct? I think people have been kind of comparing the state of quantum computing right now to the state of kind of machine learning and AI at the beginning, like 10 years ago, 2010, 2012, correct? So at that time, a lot of data came available, a lot of hardware came available, and a lot of interesting algorithms came all together. And I think actually, as Krista just said, correct, we have plenty of interesting problems, correct? Especially in the simulation area, material sciences, and many of the examples she gave. So I think there is the data, the problem set is there. I think, the hardware is coming, correct? I mean, every year people are building larger machines, better machines with lower error rates. Yeah, we have quite a few online. Others have them online, so people can actually run on real hardware. There's still small problems, but it gives people the ability to start and experiment. And I'm by no means an expert, but I've really been pleased to see many of the algorithms that in the kind of algebraic spaces, in the search spaces that we have been banging our heads again in that are all NP complete and very painful in the EDA space. Some of them have very creative quantum solutions, right? And I'm not sure I completely understand and appreciate them fully, but I think there is, if that comes to fruition, there is some really, really nice space. So I think that altogether, warrants this enthusiasm. And I said, people, students that listen to this panel, I mean, this is the decade to get on board. This is absolutely a great time to get on board with quantum.
You agree, Austin, or anything to add on that?
I would probably come from a different angle rather than the applications, the hardware. I mean, it is very difficult to control quantum mechanics. It's very difficult to build a large-scale quantum computer. But over the last decade in particular, people have started to be able to do this, build larger systems of qubits, get quantum gates down to very low error rates within striking distance of where they need to be to even justify scaling up. And it should be stressed that right now we still are at the research phase of building a quantum computer. We can't buy any hardware anywhere in the world and say, all right, it's just a question of money, let's just go build it. We still need to get those error rates lower, but at Google, for example, it's about a factor of 5 lower. It's not 100, it's not 1,000. So when you get in an academic lab results are within striking distance of where you would need to be to do this in industry, it's reasonable that industry says, okay, you have a proof of principle, now let's put some more money into it and really push.
Okay, so let me quickly summarize. So what I've got from you, the reasons why quantum computing has momentum right now is, on the one hand side, the need for certain applications which can be solved faster or efficient, more efficient with the quantum computer, that we're gonna have the prospect that the hardware is going to be available, the scalable hardware is going to be able, the limits of conventional computing, and what you just mentioned, Austin, also that we manage the difficulties of quantum computing as in a nutshell. That's sort of what I take from your responses. If I would like to quick round again with all of you, what do you think is the most important thing? Is it the application? Is it the availability of the hardware? Is it the limits of existing computings? Or is it that we handled the complexity and the difficulty of quantum computing? If I may ask just very quickly, Krista, what do you think is the most important, or all of them important, in the same fashion important? Or what do you think is the triggering this whole development most?
Yeah, I would phrase it as it's the potential to remake the global economy.
Okay, Leon, what do you think?
Yeah, but I think without the hardware, it all falls apart. Yeah, I mean, it's like AI, you could simulate and run it slowly and run it longly for 2 years. Here, I think without appropriate hardware, it's very difficult to bring the story together. So if there's one ingredient, I think it is basically really the continued progression of hardware and the software close to it that makes these machines bigger and better.
And Austin, what do you think?
I think we have a good suite of applications already with reasonable overheads to shoot for, around the million qubit level. So now, yeah, the big missing piece is the hardware. You have to get the error rates down and then scale up.
The hardware thing. Okay, this actually brings me directly to the next question in this regard. We see this momentum. Do you think this momentum is sustainable? Do you think this is sort of sustainable in the sense that we are really now achieved the breakout and everything else is just making it a little bit more scalable? Or do we believe that we enter a new of quantum winter, or that we sort of, everyone is excited and 5 years later we figured out, okay, it's more complicated than we thought and we need another 20 years? Or so we have seen similar things in artificial intelligence, for example, right, which has its ups and downs. What is your feeling about that? And maybe this time I do the other way around. I start with you, Austin. Do you think this is sustainable, or what is your feeling about that?
I do think it's sustainable because we have very concrete goals. We know that in simulation with 1 million qubits, if they've got error rates around the 10⁻³ level, you can do some very interesting things that we would like to be able to do now. And that situation is only going to improve. So I don't think humanity is going to give up on trying to build a quantum computer. It may well take more money and time than we expect. That would be normal. But if I can refer to, say, something like fusion research, the promise is there, the goal is concrete, they know what they need to do, and they've just stuck at it, whatever it takes. I think a very similar situation could occur in quantum mechanics. People will keep pushing. They know what they want. They'll get it eventually.
Leon, you would agree?
Yes, I think there is a pretty good roadmap for the foreseeable future. Yeah, in IBM put out a roadmap about a year and a half ago, where we are scaling a couple of 400 plus qubits, 1,000 plus qubit machines in the near term. Clearly working hard on error rates, working very hard on coherence times, which are prerequisite. It's not just the number of qubits that you have. And we are looking to basically combine several of these together in a larger setting. We have been looking at significantly larger refrigerators to potentially put them in and put them together to kind of get to the sweet spot, correct? That Austin pointed out. Hey, if we can get 1 million of pretty good quality qubits, very interesting things can be solved. So is it going to happen in the next year or two? No, but I think we will be getting to 1,000 bits very, very soon, and then we need to figure out how to scale from there to get to 1 million to take on some of the real challenging problems here.
So, Krista, will be you spoiling the party, or are you as optimistic as Austin and Leon?
Well, I think I share the optimism. I think the momentum is sustainable. I think with the important, caveat or, asterisk that we realize what the goal is, right? That we all agree that we need to continue to scale the system up, scale the hardware up to enable running these types of applications we hope for, right? The goal should not be to stop at NISC hardware. We need to really sustain that momentum all the way through to a set of milestones that focuses on scaling the whole system up to achieve 1 million qubits. So NISC is not enough. I think we'll see if the other panelists agree, but I think at this point we don't see value coming from NISC applications. So we need to keep going.
Austin is nodding. So everyone is very optimistic. Maybe final question for this segment. If there is we're all optimistic, that's great. But if there's of course, there are a couple of roadblocks and obstacles on the way. What do you believe is the biggest threat, the biggest roadblock which we have to overcome? Whoever wants to go first.
I mean, for me, it's all the hardware challenges. There are some very simple things that are tough to deal with. Cosmic rays, if you have a superconducting computer, are tough to deal with. And that is just one of many challenges that remain to be solved at the engineering level. The need to recalibrate. It's not easy to build a quantum computer. The devices that you build don't hit usually the spec that you request, and even what they do hit can drift, and different parts of their performance can become better and worse over time. So it's a big challenge to keep all the pieces working well from time of manufacture and throughout the lifetime of that processor. So, we can't claim that there's no engineering risk. We're certainly hopeful that it's manageable, but there are still big challenges to overcome.
Leon, Krista, anything to add on challenges and roadblocks?
I mean, I think Austin is very right. In fact, it is the challenge of building reliable, reproducible hardware that keeps on running. Right? So I mean, that's one of the reasons we have been trying to at least put out a good number of machines there and kind of push the engineering progress is exactly to start to learn a little bit what these effects. Right? What does it take to calibrate and recalibrate a machine and keep it going? Yeah. What does it take to kind of run an alternating software stack on there where different problems get shot at it every couple of minutes, every couple of seconds. So it is a huge engineering challenge, right? It is an enormous engineering challenge for just about every angle you look at it. Not just getting enough qubits together. Because we have sort of this inherent conflict, right? On one side, qubits love to be very isolated, well controlled, not disturbed. Yeah. On the other side, you want to compute with them and you want to measure them. Yeah. You want them to interact fast. Yeah. So it's very difficult to get a balance right and keep it right over a period of time so that you can do meaningful long computations. So it is, I think it is great to see that there are many different approaches currently being pioneered by larger companies, by startups. So if some of them fail or have some advantages versus others, you see people zigzag. So I think that's the way great engineering problems get solved, is people looking at it from many different angles. So while it's tough, I think there's a lot of people looking at different pieces. So there's continue to be some really good opportunity.
Perfect. I was about to say, okay, at the beginning you mentioned hardware is everything, and that's the reason why we got this momentum. And at the same time, this whole discussion on obstacles came a little bit across that hardware is also the main obstacles. But now you brought up also these other things, like we have to make that it's a large area with lots of problems. That's great. We've got for this particular part here also a couple of questions from the audience. I see that in the text chat, and maybe I can call on Mike. You have one question to Austin, right? Mike,
sure, or maybe for the panel as a whole, actually. And Robert, I think you even sort of touched on this in one of your follow-up questions, but I believe that Austin mentioned that Google is, say, 5 times away from where we'd like to be to have impactful hardware. Would others agree or disagree with that based on sort of different hardware implementations you're looking at. I'm just curious to get a perspective from, these industrial experts about, where we're at on the roadmap.
Leon, Krista, maybe?
I think, Austin, you were referring to some of the error rates, correct, that you're seeing where you're starting to be in a reasonable distance, correct? Not all.
That's correct. Yeah, if we could take our
the
existing error rates and reduce them by a factor of 5, would be done. We would just focus on scaling from that point.
Yeah. So I think that's Mike. So that's on metric, correct? That's very encouraging, correct? Then we need longer coherence time to run longer computations. Yeah. And we need more and more qubits. I think that's what Austin calls scaling. Yeah, and we need to do that at the same time by not messing up the other metrics. Yeah. So I think each of them, some approaches have advantages, in the hardware from one of the angle. Yeah. I think the trick is to get to a hardware approach that adds them all up, correct, and scales, which is interesting. Yeah.
Perfect.
Yeah, I think it's important to look. I think the reliability of the qubit or the fidelity is just one parameter of the equation, right? You have to have good reliability of the underlying qubit technology or qubit design, right? You also need the right size. And then you need the right speed. So ultimately, we're going to look at wall clock time when we look at applications. So we need a qubit and then corresponding system that enables the right wall clock time. We want solutions that come out within a matter of weeks, not a matter of years, right? So that whole system has to have a fast enough operation speed at that logical or algorithmic level, at the wall clock level. Then I think that reliability, to Austin's point, having it 5x better, yes, that can work, but then that comes with additional challenges, right? So I think we need, if we can do better than that, it comes with hurdles. If you only have 5x better, I think then you need a pretty substantial control and readout system, and how are you going to scale that up? So, I think as Austin, you said, right, then you need to focus on scaling the rest of the system. And that has a set of challenges in it as well, right? We can't have millions of wires running into the fridge. We're going to have to scale in different ways. We're going to have to find out different ways to control the technology and then have that readout maintain speed. Again, going back to that ultimate wall clock time. And then you also need size. So the size of the qubit matters, right? We need to build something that's going to be reasonable in size and doesn't, come out at the size of a skyscraper, right? We need something that's going to be able to be embedded and integrated in our data centers, into our cloud systems. And so it's important to look at all three, I think size, speed, reliability as the three parameters when we look at a qubit design and then corresponding system design.
Perfect. So let's do 2 more questions on this general quantum computing part, and then we move on. The first question is from Marcel Walter. Can you state your question, Marcel? Has to find the mute, but otherwise I can read the question maybe. So Marcel is asking in the text chat, is there some scaling similar to Moore's law becoming apparent in quantum already? Anyone who wants to quickly address that? Do we have a Moore's law equivalent of in quantum computing?
I guess I might. Yeah, I mean, certainly there is this metric called quantum volume, that we have proposed, others have adopted. That is an interesting metric that measures the quantum computer in various attributes. And clearly that could be taken, hey, if that is a good scaling metric, would that be something that we want to drive up as Moore's law, correct? So I think there are other metrics, but I think people are starting to look at this. What is exactly the right equivalent? It's not just the number of qubits. It needs to be a significantly more encompassing metric. And quantum volume is one of them that could drive kind of a Moore's law type of scaling for quantum.
Perfect. Asking for a very quick answer, Austin and Krista, what do you think about the quantum volume metric?
I feel it's mostly NISQ focused, but obviously one day if you had a fully fault-tolerant computer, you could also continue to use quantum volume just at the fault-tolerant level. It's not certainly what we optimize in our hardware. When you have a 2D nearest neighbor grid of qubits, this is not optimal for getting the most out of quantum volume. So, at the moment we focus on the stability and error rates of our devices. We're not really at the scaling stage. So I would argue we don't have a Moore's law yet. But once we get to qubits that we can say that's good enough, let's just preserve that performance, you could start hopefully building such a law, which is really, can you double the number of qubits over some reasonable, frequently repeated timescale? I don't think we're there yet.
Krista, any comments, additions?
Yeah, I would agree on that, we're not quite to the realm where, really taking a Moore's law or a metric that makes sense here and looking at its doubling roughly makes sense yet. I think we definitely need to get to the logical qubit level there and make sure that we're looking at a doubling that impacts right at that framing we care about, right? The logical algorithmic level. And I think quantum volume is an interesting metric. I think it's not the answer. It helps us get to a logical qubit. But again, I think going to the first part of my response, right? When we get to that logical qubit, I think we need a different set of metrics to be looking at.
Perfect. So it really seems that this alone on quantum computing in general and its development, we can spend an entire panel on. Let me close this segment with allowing one final question, again, asking for a brief answer, and then we have to move on to the next segment. And this question by, I hope I pronounced it correctly, Ulya Kaputsko. Maybe if you're able to unmute yourself, maybe you can quickly ask a question.
Sure. So we often hear comparisons of quantum computing to classical computing in 1950s, where the building block, the transistor existed, but we didn't have the system stack. And then there's another camp. The comparison is rather to 1930s of classical computing, where we didn't even know how the building block, be it transistor or anything else, should look like. So I just want to hear about the opinion of the panel about these comparisons generally.
Who wants to start?
I would agree with the 90s, 30s. We don't have performant quantum hardware yet, right? So we still need to build that fundamental building block.
Leon, Krista, you're also with the 1930s or more with the 1950s?
Well, I think neither is a perfect analogy because today we do have the advantage of having very large scale classical compute, right? We have entire clouds and HPC at our fingertips. So we have the ability to bring software in and use software to our advantage to understand how to architect. I mean, to the point maybe of this conference, let's really co-design and co-develop what the system should look like for the workloads we want to be able to handle, and use the classical compute and software to our advantage to bring about a more rapid evolution or maturation of the technology. That didn't exist in either the 30s or the 50s. So I think we really should position ourselves to bring about a new way of co-designing while we're evolving all the technology and components.
Perfect. So I'm directly picking that up in order to ease into our next segment, which is actually about these kind of questions, which is about design automation for quantum computing. So now we've got your views on quantum computing in general and its development. That now, of course, this topic is also a huge topic in the design automation community, as it is probably in the software engineering and programming, of course, physics, theoretical. So every community sort of starts to get involved in quantum computing. But this is a design automation conference, and obviously the audience here is particularly interested in the contribution and the developments the EDA community can do in quantum computing. And as a starter, maybe Leon, I start with you. Can you name any particular accomplishment, achievement, or anything where you believe, okay, this would be this is what the quantum computing community could benefit most from design automation? What comes to your mind?
Yeah, so the most, I mean, I think there is the interesting opportunity, I think, for the EDA community to participate in many parts of the quantum stack, right? I think as Krista just said, I mean, I would say we are probably in the crazy 1960s here, yeah, because the fundamentals might not be entirely right, as Austin pointed out, and we need to kind of get the right EDA tools in place to really get the fundamental building blocks better. But at the same time, we have like this crazy stack build up, through software, through assembly, through compilers, performance libraries, some applications that people can actually work on many layers of that stack here. Yeah. But starting from the bottom, I mean, classical EDA, correct, is really about how do we make chips better? Yeah, how do we make electronic systems better? So there's tremendous opportunity because I mean, qubits are very finicky. Yeah, so it's extremely difficult to figure out what is basically starting from the basics, a really good layout for the systems. Because if you connect too many of them, you get way more possibilities for errors to go across. Yeah, if you connect too few of them, it becomes very difficult to do meaningful computations, right? Because you have to constantly move qubits before you actually, Robert, you know it well, because you wrote one of the first transpilers dealing with this, but you're moving more qubits than you actually get to a final compute, So basically getting to a trade-off, which is really what EDA quite often is about, by having the right models, the right, I would say, device models, or models what is going on with the underlying simulations, the electromechanical, the electro RF simulations, what causes the crosstalk between the qubits? If you lay them out slightly differently, how does that affect kind of their behavior? How many do you connect? Correct, that kind of comes together in the chip design. And so you need to kind of the tops-down information from the compiler. I mean, how much can an optimizing compiler do? For particular algorithms that we are predominantly interested in. Correct. What type of connectivity would we like to see? That allows us for an interesting algorithm to be solved and enough error correction to be applied there. And at the same time, bottoms up, what can you actually build that doesn't create enough crosstalk and enough disturbance to begin with? So I think the EDA problems are at the bottom, very traditional EDA problems. And tops down is basically, it's not really a compiler, correct? It's more like FPGA, place and route and synthesis, where you're really trying to put specific logical bits, in particular qubits, to make sure you have the best chance of success for particular kernel of an algorithm to succeed there.
Perfect. So you mentioned a couple of problems where design automation can help. Austin, can you would you agree with this selection? Can you add further problems where design automation expertise can help? Would you like to add something?
Sure. So that's a good start. The list from Leon. Some extra ones. For example, when we lay out the wires and even the qubit positions on our chip, it's still a fairly labor-intensive process. So there's a lot of scope to build tools that help people designing these chips. It's very, very much in its infancy. When it comes to calibrating the quantum computer, we have a lot of software, but it's certainly fair to say that it hasn't had a great deal of disciplined professional software engineering attention to it. And that is definitely something that will need to be done in the future. When you calibrate one of our qubits, there are about 50 variables that need to be set for every qubit, and they can drift, and it is very, very complicated. And while we have a bunch of physicists that understand all of those variables and are very smart and code quite well, it's still not the same thing as having a group of professional software developers that can really try to push that further and make it more user-friendly. It's not at the moment. We have a handful of specialists that can get our qubits really singing and dancing, and everyone else sits back and waits for their ability if they want to do a good experiment. So that needs to get a lot better. When you build a chip, even after you've done your best, there will be great variability in terms of the performance of every qubit and every gate between every qubit. And that's, of course, information that you would like to use in a nice automated tool to say, well, where should I put my circuit? What gate should I be using? Which one should I avoid? Which one should I not? Again, software to do that is still in its infancy, so there's plenty of scope for getting better. And the further you go up the stack, of course, as you have more qubits, the more opportunities there will be to bring professional design automation engineers into it. So this is just where we're currently working at, but one day when we have more qubits, you'll be wanting to program not at the individual gate level, okay? We need to build more and more layers of compiler up, and some of those tools exist, but there's always a lot of opportunity to optimize for any particular piece of technology. So, there is a wild field of potential collaborative opportunities.
Krista, would you concur? Would you like to add something?
Yeah, I think this is a great list from both Leon and Austin. I would add, in our, for example, the type of technology we're working on in a topological qubit, we have a very different set of materials there, a very different stack. And so we've worked to develop a whole set of modeling and simulation tools, verification, validation, benchmarking tools, tuning tools, right, and techniques. And I think as was just highlighted by Austin, right, much of that is done, by physicists. And there's a great opportunity there to bring that software know-how, the EDA know-how, forward to that, to see how do we speed it up? How do we make it more predictive? How do we automate that? How do we make it more end-to-end? What should tuning look like? What does boot look like? Like, how do you boot a quantum computer? How should you boot a quantum computer? I mean, we can turn small ones on, but when they're 1 million qubit large, what does that mean? Where are the expensive steps? How do we automate those steps? We don't even have a great set of benchmarks right now. I think even to the earlier conversation, is quantum volume a good metric, right? Ideally, we would have a whole set of benchmarks, and many of those are going to have to be tuned to the type of qubit when you're looking at that chip level validation and verification, for example. How do you debug it, right? How do you know where things fail? All of these questions, right? We have some good answers to some and some developing answers to others. But I think, across all of that, we just need a better set of tools, some which will be very hardware focused, specific hardware targeted, specific architecture targeted. Others may be more hardware agnostic. But we need more people coming together to look at how we bring those tools forward so that we can achieve more rapid acceleration on the maturation of the hardware.
Perfect. Yeah, you mentioned, and this is also related to my next question a little bit. Where are we here right now? And you mentioned we have some good solutions and some how did you call it? Some developing solutions, something like that. And do you also believe we have some completely wrong solutions? So are you aware of? And I mean, of course, you should not name any particular, but is there a particular direction where where the design automation community is going in the completely wrong direction? Anyone who dares to speak out now, or are you too polite to in this audience?
Perhaps you could list some of the directions you feel the design automation community is going in.
Pardon?
If you wish us to give feedback on the directions that have been taken, it would be really helpful to get a list of those.
No, I just let me put it the other way. I often have the feeling when I work, but let me use myself as an example. When I work in quantum computing, sometimes, of course, we heavily rely on models which have been given to us, because we are all no physicists and we hardly sort of understand the specifics of physical constraints and related. And how often do you think happens is also I often have the feeling that I'm not sure we have this model. Is this model trustworthy? And how often does it happen that we're developing really ingenious solutions for problems which, however, don't really exist for an actual quantum computer? Does it clarify the question a little bit? Is this happening on your view? Have you seen something like that? Or do you believe everything we've developed in the design automation community so far was perfectly on spot what you as quantum computer expert need?
So on that specific question with regards to error models, it's certainly true that most of the literature will use a very simplified error model. And I would argue that this is not the wrong thing to do, even though real devices have much richer, more complicated error models, because the goal is for the hardware to control the richer error model and deliver to the next layer a simplified model that is good enough. So, we do have leakage, we do have crosstalk, we do have cosmic rays, we have all sorts of drift and other things that are in there. And no, those are not typically modeled by people, but that's okay. So I would say that is not something you should consider as wrong on that particular topic.
because it helps us at least developing in the right direction. And once we have the more mature models, we can then accordingly adjust the solutions we developed so far, right?
And also at the hardware level, you try to deliver something that actually matches. You build hardware that matches the theoretical model. We have leakage. What does that mean? We don't have qubits. We have multi-level systems, and they can leak to states 2, 3, 4, and so on. This is, of course, not typically modeled in the literature. However, that just means at the hardware level, we need to reset qubits regularly so that you can ignore that fact. It's like the whole reset process and leaking process is just not something you need to model. So, that is explicitly our goal, to build the hardware that then matches the theory. After all, the theory came first. We had algorithms, then we had error correction, and the error models theory. And then the goal is, can you build hardware that matches the theory? So, and to a large extent, we believe that is possible. It's still a work in progress, but that remains the goal.
Perfect. Maybe to be a little bit more provocative, maybe Leon, your comment on this one. So literally most of the work the design automation community has done in this direction makes sense, or at least helps us to understand it, or what would be your take?
I would say it makes sense, but it does not necessarily be fully accurate or fully to point. I mean, we have chosen, to build, basically the whole stack kind of in parallel, right? I mean, we could certainly go and say, hey, let's build hardware, try to get really good models, and just very slowly work our way up the stack, right? That's basically going back to the 30s. Maybe we get there, by the time we get to the 60s. Instead, I think what's exciting about the current development is that we picked a lot of layers of abstraction. And I think Austin already pointed out the points where they are not perfect, right? Or not, they might even be slightly wrong. So we need to make them better, correct? But therefore, it's great to see various open source frameworks out there, like Qiskit just being one of them, which has abstraction layers at various layers, allows for mapping to different hardwares. Clearly doesn't capture all the effects. Actually, many of them need to be upgraded every iteration. However, by able to refine these models at each of these layers, people can work at their level of the stack and make progress. And therefore also, which I tried to point out earlier, pass information down the stack, right? Basically, what can be solved, above the assembler language versus what absolutely need to be solved in hardware, and where can we meet each other so that we make this incredible hard job of making hardware, at least as easy as possible. I think so that's where the top down helps a little bit too.
Perfect. Since you mentioned open source, maybe also a quick follow-up on that. In the conventional realm, of course, we have open source software there as well, but most of the really powerful software is not openly available. And it's actually the business model of major EDA vendors in this regard. In quantum computing, it's a little bit different, but there's lots of open source available. Do you think this will remain? What would you think is the main business model? More the access to a quantum computer and not so much the software to use it, or will this also evolve later on that also the software is going to be a business model on its own? Whoever wants to go first.
Well, I think in general, on the upper layers of the stack, right, we definitely see a big move to more open source software. Microsoft as a company is, very much adopting that model and producing a lot of open source software. I think the other two companies on the panel today are in a similar position. The value comes from using that software on particular instances and customizing it. And I think the value from a quantum computer is really going to be in the solution ultimately, right? And so we believe that, on the upper layers of the stack, that open source, supporting the open source community, enabling people to have at their fingertips the ability to come up with new solutions, new algorithms, to try it out. That's very, very important to kind of seed the level of innovation we need around quantum algorithms and applications. Now, with that said, as we go deeper into the stack, I think the reality is the development of large scale systems is going to happen at larger larger companies, right? This is going to require a very, very large investment. It's going to be large entities that are operating in that space, and naturally, as you get closer to the hardware, it becomes more proprietary. So there, there will be a need for very custom, proprietary, I'll call it proprietary software, right, at maybe the lower levels of the stack. But I think it's interesting to see where that can come together. What abstractions can we put out there so that we have a lot of good creative new ideas coming from from the open source community, academic community, research community, et cetera, right? How can in order to speed up innovation across as we go to scale. So I think with that, for example, we've put out something called a quantum intermediate representation that's built on LLVM in terms of open source compiler tools, right? And we hope that this intermediate representation enables people to work both up from that representation, right? Look at different representations at the higher level of the stack, the user level, different high level languages, for example, work on compiler techniques for quantum. And then at the lower levels of the stack, hopefully then people could even write their more proprietary or custom or hardware targeted software right up to QIR. So we hope that this representation enables innovation on both sides of that intermediate layer.
Leon, Austin, anything to add?
So I'd certainly echo that, and I would point out that at the moment the line of where we open source is very, very low. We open source from the circuit level. We have Circ as our open source tool for programming a quantum computer. Outside users have certainly used that. It's hard to imagine going any lower open source, because then you're really directly dealing with calibration of the hardware, which, as I've mentioned, is very, very difficult. So yeah, everything above the hardware level is open sourced, and the plan is to continue to do that.
I think it was interesting that you mentioned the EDA companies, right? Because if you go back into the history of semiconductors, the original companies like IBM, AT&T Bell Labs, Philips NetLab, Intel, Siemens, they had their own EDA organizations, right? There were nothing like EDA companies till the 35, 40 years ago. Right? So then when sort of the chip design came to, a level where standard cell libraries kind of became a good abstraction, and layout became standardized, thanks to Mead and Conway. Suddenly independent EDA companies started to spring up and became kind of private companies that owned a good chunk of the stack here. I think here, as you heard from Krista and Austin, we're starting completely in the opposite. Like we start pretty much with an open source stack, that everybody's trying to go as deep as possible, before you get too dirty into the hardware by putting the right layers together, including almost steering the hardware at the pulse level. So there is right now a really nice amount of openness in the industry that allows for a lot of experimentations to take place. Clearly, when the hardware becomes more complex, probably certain more layers lower up need to be kind of locked in one way or the other, and tied very closely to the hardware. But I think you have a very different dynamic than we had in the beginning of CMOS and semiconductors and the EDA industry at that time.
Maybe last follow-up on the segment, and then also the reminder to the audience, if there's any question, just show that in the chat. Leon, you just said that open source is if I got you correctly, is a huge trigger for your developments. Austin, Krista, is it similar to you? Is it a nice to have? Is it a must have? Is it something you understand that's happening, but you are not that much influenced? How much is the developments by the scientific community or by the open source community influencing your work?
So when doing open source, the best way to do that is in collaboration with the community. So certainly Circ is an example of that, and Open Fermion, Open Ising. We have very deliberately collaborated with the community on these projects and plan to continue to do so. So it's very important. The engagement not only gets the tool built, it gets the tool used, it gets ideas generated, and that is planned to continue.
Krista, any comments on that?
Yeah, I agree. It's really important that when we're looking at open source software, that we're doing that with the community. I agree with Austin there. I think as an example of that, we've just joined, for example, the technical steering committee of Open Chasm, right? Again, hoping to work with the community on developing tools and languages and representations, right? We're also, as I mentioned, forming QIR as a community-driven, representation, so that the community can really elevate that to what it needs to be for innovation to happen on both sides of that layer. And in terms of the, I think Q#, we have a high-level language, Q#, really focused on more scalable algorithm development, although it can be used for hardware today as well. I think there again, really looking to the community. What are your needs from a high-level language? How do you want to see it developed? So I think that's, open source is definitely a huge investment for us, and something we really want to see, driven with and by the community.
Perfect. Then let's see. We have two questions from the audience. Ulia, you go first. If you can unmute yourself.
Sure. So quantum computing at this point is relatively mature, but we are talking about abstractions. So the question is, can't they be evil in that they mask important details to guide establishing an efficient system stack? What would be the right balance?
So as mentioned, in Google's case, we go all the way down to the circuit level. We don't go down to the pulse level because in principle, you can tune knobs and apply pulses to our qubits that would blow them up. It's really that simple. So, we only let people that really know what they're doing go down that level.
Yeah, I would say in terms of which abstractions, right? We have abstractions that layer from the high level all the way down to the lowest level, right? The metal, if you will. And some of these abstractions are exposed to higher level users, and some are exposed more to an admin level control, maybe to Austin's point, right? But I think the role of abstractions is really critical. At least I was trained in more of a compiler setting. My advisor in graduate school was Al Aho, just won the Turing Award, right? And he constantly spoke with me every week about the importance of the right abstractions, right? Setting the interfaces, discussing the abstractions, having many layers of abstractions. So, I recognize and value your comment. At the same time, I think if we're finding we haven't had the right level of, the right abstraction defined, we should either split it apart and define, two more right ones to slide in, or adjust the abstraction, because I think abstractions are critical for helping us understand how these components fit together. And then also for building all of the tools, the transformations, the optimizations, the readout and control and signal processing, right? All of that, we need to make sure we can come together and bring many different people from very different disciplines together and write all these components. So I think I see the abstractions as absolutely critical.
Very well said. Yeah, the abstractions are absolutely essential. Yeah, I think the only thing we need to watch out for, I mean, there are two reasons people make abstractions. Right? People make APIs and they become golden and nobody ever wants to change anymore because they build so much stuff on top of them that they get frozen. That's not the case here, or we should prevent that from happening, correct? The APIs in this area, yeah, the abstraction levels will continue to evolve very rapidly. Yeah, but they are essential. Yeah. But make sure that you can, deal with the change that will be constant for a long time to come here. Yeah, because we don't know exactly what to abstract yet in what way, shape, and form. So there will be pretty rapid evolution here. Yeah, until we get to Austin's big 1 million qubit error, or a very low error-free type of machine. Yeah, these abstractions will evolve very, very rapidly. So as long as we don't lock them down, they won't be evil. Yeah, they will be very helpful.
And perfect. Also bridging for our next segment, you mentioned that these abstractions are good to bring the different communities together. I think as we talked about also earlier, a lot, do we have to write models? Do we have to write metrics? Of course, we need these kind of abstractions, these kind of models, metrics, so that different communities can work with. However, I also would like to have a little bit more critical view on that, because right now, at least my feeling, please feel free to disagree, is that lots of communities are working on that right now. We've got software engineers, design automation community, physicists, people from theory, and so on and so forth. And at least when I try to check out other communities, other conferences, I frequently see they literally solve the same problem or similar problems, and there's hardly any interaction between that. And my question would be, is this actually a good thing? Because then this way we get different views, different angles on those problems, or is this a bad thing because many people are doing literally the same thing, but in different communities, and there's hardly any exchange? How would you use? How is this just? I would say a natural development, but is this good? Is this something to keep going because of the different angles, or should we try? And if yes, how should we try to have more interaction between these communities? I don't know, Austin. Maybe you can address this first.
Sure. I think it is just the way the world economy is set up. In principle, if you wanted a quantum computer in the shortest time with the minimum dollars invested, then yeah, you would pull a lot more resources than we do. But competition drives investment. People like being the first to something. Competition drives effort. Researchers like being the first to do something. And, when you have many different groups pursuing things that normally look like exactly the same thing, they don't actually all do it in the same way. IBM and Google are both investing superconducting qubits. But if you look at the details, they're actually very, very different under the hood. The techniques, the approaches, the couplings, it's all very, very different. Exactly how it's built at the fab level is very, very different. So, it's the way we do business. It's always going to be this way, and I don't see it changing for a very, very long time. And I think it is the right way to really work out how to build a quantum computer, have many people competing to do so, to have that excitement. It does add a lot to the whole community in terms of shaking out new ideas and new ways of doing things.
Mm-hmm. Krista, what do you think? Good to have these different communities working on similar problems?
Yeah, there's definitely value in having, having similar problems be tried by different communities, right? You will, I think, in the end, develop different solutions. And so agree with what Austin said, but I also think there's an opportunity to bring more people together and learn to communicate across communities, so that we can learn from each other, see it from different angles. I think one thing with, just as we discussed, open source software, right? I think that brings, if you're looking at contributing and leveraging an existing stack or an existing representation or platform, right? Whatever it may be, I think if you contribute back, right, that helps other people learn. It helps us, and that, then make progress from there. So I think if we can continue, while the competition is definitely healthy, I think it's also very healthy to communicate with each other and see where we can leverage these new ideas or how we can contribute it back to something that can be leveraged more widely.
Leon, your take?
Yeah, I think co-opetition is healthy. It's good. It's both, as Austin said, from the business side as well as in the research side. Yeah, if people come from a slightly different angle, solve the same problem, at least they both understand it now. Yeah, and if they get the understanding, that actually they ended up at the same point. So I think for now, I mean, we are. I don't know. I read some articles somewhere. We have like 3,000 skilled quantum workers, whatever you want to define it. Right? It's very small people. Yeah, so more people that are willing to play with this, try to understand the abstractions, be creative with this, maybe solve a problem somebody else already solved. At least then they have mastered it to a level that is probably good enough to kind of take the next jump up from. So right now, I think it is just, it is basically the state where we are. Yeah, we are far from done. Yeah, so it's chaotic. And if you are a creative researcher, no matter if your background is in compilers, if you are quantum physics, you're in chemistry, if you're in engineering, I think everybody can contribute. Yeah, and the key is to find people that can bridge these communities, can actually build and refine these abstractions that allow for communication to take place between these groups, and basically grow the number of skilled professionals that can deal, in the quantum, worker sphere. Yeah, I think that is the most essential, for the next decade to be successful in this space here.
Perfect. Maybe also talk a little bit about that. How do you compile your groups to, within IBM, within Google and Microsoft? So because as I said, we have different backgrounds. Do you put people from different backgrounds into the same group, or just from the so how do you do that in your developments? How do you compose your groups together? Whoever would like to go first.
I think that question can't be answered without reference to COVID. This has really changed the way our group has been structured. Almost everyone is still working from home, and it's not clear when that's going to change. So, at a certain level, the only groups that are together are those that are directly touching the hardware, which is a small fraction of the total group. Everything else, we are still trying to get creative in terms of making sure ideas are shared and sufficient contact is kept between group members to keep the research cohesive and moving forward. It's an ongoing creative challenge, trying to make the right environment. It's something we struggle with every week.
Krista, what about you? Your groups, like how do you compose them of groups with similar backgrounds or with completely diverse backgrounds?
Well, I think diversity is very important, right? When we look at solving a challenging problem, we need expertise from a variety of backgrounds to make progress on solving that problem. And so in terms of our overall quantum program, we've definitely looked to make sure that we have a diverse set of expertise around the table. And I think in terms of bringing such a diverse group of people together, it's really important to have a shared mission, right? What are we working to achieve together, and work on having clarity around that mission, and then of course road mapping. What are the steps we need to take to achieve this mission? And so I think that's one of the things we really focus on is looking at this shared mission of achieving what I would say an industrial scale, right, or a leadership class quantum machine that's able to solve these very, very challenging problems that will have an impact on our society.
And Leon, how was IBM take on that? IBM's take on that?
Yeah, IBM's interesting. IBM from the start started to run this quantum program extremely multidisciplinary. Yeah, all the way from basically people kind of working, with other research institutes like that wanted to kind of, simulate batteries, or people in the financial industries that have key optimization problems. So people that kind of have domain experts in their algorithms, down to people who could kind of are very well versed in compilers and compiler optimization, electrical engineering, CAD people, chemists, physicists. So I would say IBM took pretty broad kind of look across the corporation and put a lot of people together from very many different disciplines in the quantum team. And at the same time, kind of try to build a quantum network going out into research universities, with different hubs, into clients to basically even pull in and drive more, I would say, multidisciplinary expertise. So I would say, again, trying to work across the whole stack in parallel, bring a lot of these people together. Sometimes very difficult because we speak all different languages, not just Dutch and English, but all type of different layers in the stack. So it is sometimes very, very tricky. Back to Austin's point, it is though interesting, correct, that COVID has really leveled the playing field for many people to contribute. Where in the past, if you were in the meeting room where mostly chemists were available or quantum scientists was difficult to, now by different people, different groups, meeting in different chat rooms, different places, there's actually a lot of interesting discussion, no matter where you're sitting, where in the globe, as long as you want to wake up at the right time zone. There's a lot of phenomenal collaboration ongoing that we have to see kind of how long that's sustainable, but driving very, very different discussions than that were not happening a year and a half ago.
Interesting to see these positive side effects of a pandemic. Coming back to you brought up common language. It's also a topic I would like to briefly discuss with you. Common language. Do we need a common language between those communities? What do I mean with that? I mean, just alone on, we talked in the past hour, we talked a lot about compilation, but actually over on this process, we have different terms. We have the term compilation. Some other groups call it synthesis. IBM called it transpilation. At least part of it is transpilation. Mapping is used. And this is just alone for the process, not even talk about different models or metrics again or so. So I would say we don't have a really common language. Another nice example is also when we talk about quantum computing verification or quantum circuit verification. The term verification has different meanings. And when I am in touch with people working in the areas, we usually have to spend the first amount of time to really, checking what different interpretations of words we have. So I would say that's a problem. Would you agree? And if yes, how do we overcome this problem? Is this something where we need to define a common language, or is it not such a big deal as I'm making it of? What do you think? Whoever wants to go first.
I think historically this is an issue that afflicts every new field and gradually sorts itself out as people write textbooks and become bestsellers or don't. Even in error correction, people will define words to mean exactly opposite things at this point in time. And so you always, as you said, read a paper with the first part, what do you actually mean, and then read the rest of it for the content. I don't think there's any way you can stop people inventing new terms that have already existed and not realizing it in conflicting ways when a field is so new. So it'll sort itself out. It always does, sooner or later. In the meantime, we have to deal with the babble of confusion.
Leon, Krista, would you agree, or could we do some more efforts, or maybe just write a book trying to define it, make it a bestseller, and then we solve the problem?
So you're taking my answer. Exactly. I think Austin is right. It's a sign of the time, but this is the perfect opportunity for some people who can take half a step back and say, okay, these 5 people call this 5 different things. It's really the same thing. Let me pick the best term and write the authoritative first tutorial, first book, and write the meet and convey for quantum computing, or whatever. Pick your favorite compiler book, So I think it is actually the time. It's about right now. I think there's enough base, that you can write this, and there's enough duplicate or triplicate terminology that it's about time to clean it up. So people who can start to give real good tutorials at conferences that basically bring material together, contrast, compare, and levelize it. And professors that can do this in schools, and somebody who wants to write the first book, like I wouldn't say the definite book, but the first book. I hope to see this in the next year or two, because this is the right time for these things to start to take place in this community.
So whoever is watching this, just starting it right now, this is the time. And if you do this book, please don't forget to acknowledge this particular panel and the panelists for the suggestion, right? Maybe easing into our final segment for today, which I would like to dedicate to quantum workforce. And obviously we talked a lot about the different communities and the different players and different people who should contribute. Just straight away, how hard or easy it is it for you to find people who are interested in working in quantum computing and also have the expertise working in this field? And I don't know, maybe Leon, maybe you can start.
It is very hard. I mean, I think in general, the IT industry is super competitive. So I think all of the companies here on the screen, I think we have the fortune that I think each of this have a pretty broad workforce to tap into. That we can use from our internal teams who are excited about this, as well as have fully enough name recognition, and we can extract external people. But the pool is small. So the pool is small, and the deeper you go, the more difficult it is. So this is, I would say, I said before, but for students, this is the time, correct? So you will have a job. Don't worry, you will have a job, and a really good one. So if you are interested in this and willing to get deep in one of the areas, this is absolutely a golden opportunity.
So Krista, Austin, I guess you would agree it's hard to find people, or is it easy peasy for you?
No, it remains challenging. I mean, even at Google, where we look after our workers, you can still easily be outbid by a startup, and there are many of those these days. So no, it's very, very competitive. It is a very good time to get yourself educated in quantum, as to echo Leon. More workers are needed. There's great demand, and quantum's not going to go away in a few years. It's a long-term project. So a great place to say that's a place I'd like to have a career in. So you have time, learn, and you'll have great prospects.
And any best practices, again, whoever would like to say something on that, any best practices, how to get those experts, how to train them? Is it simply like we are here at DAC right now, there are lots of promising PhD students and candidates, you can just ask them and they will immediately join, or any best practices in order to get them on board and get them acquainted with the course, with the needed expertise and background?
So just speaking for myself, in the quantum error correction area, we look for people that have strong formal training in software engineering and also understand quantum mechanics and quantum error correction. And there aren't many of them. You know, if you already have the strong programming, there are many, many free online resources to get the quantum mechanics and quantum error correction education. So, you know, begin, really.
Krista, Leon, any additions?
I think, you know, as we look forward, indeed, you know, we have a shortage of workforce in the space now. My biggest concern is what's going to happen in a few years. It requires making sure people are entering and being trained now. And in a few years, I think the biggest challenge is we're going to have and I think potentially the biggest class of workforce, if you will, is going to be in users of the system, right? Developing solutions on top, right? At some point in time, it'll shift in that direction. Right now, we need more people working on the stack, across the whole stack, from materials and device design all the way up to the algorithms. But as we go forward, I think it's going to be people that understand how to program a quantum computer and understand a domain. So I think cross-disciplinary is so important. That's important also for the stack, as Austin just mentioned. Understanding quantum mechanics and information theory, understanding quantum mechanics and material science, understanding quantum mechanics and, right, you can go on and on across, and compiler design, right? So I think throughout we need a lot more cross-disciplinary education and engagement, and people coming to this field from many different backgrounds. And we also need to enhance the education, you know, for these different, you know, to operate in those different layers of the stack, and then ultimately also operate as a, you know, consumer or developer on top of, because that's going to be a huge shortage for us in the coming years as we scale up, right?
Okay, no, I already heard about your needs, but you know, and maybe also a little bit provocative right now, but you say quantum computing is not going away, so it's a secure job, but maybe so is machine learning, artificial intelligence as well. And some people joke, I'm not sure, but it's not my quote, but people say, okay, well, it's relatively easy to get acquainted in machine learning because you just throw data on something and that's it. I'm simplifying, of course. While in contrast, it sounds really hard to get into quantum computing because, as you say, you have to need an interdisciplinary approach. You have to have very strong formal background. That's what you said, Austin. So it sounds like it's actually really hard. Any way of sweeten the deal for potential candidates to make it?
No, I mean, if you had given me that sales pitch, I would have gone and chosen the very hard, because I was never looking for very easy in a career. So honestly, you shouldn't join quantum computing because you're hoping for an easy way in. It is a very challenging field, as is building a satellite or a fusion reactor or the latest generation of nuclear reactors. I mean, if you want easy, fine, but you know, if you want high-end, cutting-edge research, hard has to be the thing that gets you out of bed in the morning, keeps you up at night because you're doing things that other people can't do. So no, bring on the people that want the hard. It is hard. That should be what you want.
Perfect. Any additions, Leon, Krista?
No, I cannot agree more. Yeah, I think this is a hard problem, and we need, very, very smart people, people who can collaborate well, across disciplines, but also, across people. So we need a very kind of diverse set of people that are basically willing to wake up in the morning and and try to change the world. And this is a great place. Right? This is a place where you will be able to change the world, likely, in the next decade. So if that's what you're after, this is a pretty nice spot.
Perfect, terrific. And maybe at the end of our panel, maybe we can come back to the audience again and let them ask a couple of final questions. So Kevin, a while ago, already had a question in the chat. Kevin, if you're still with us, maybe you can unmute yourself and ask your question. If this otherwise, I can read it. So Kevin was asking, what is the technology and competitor that you fear the most? Kind of provocative. So we've got, you talked about competition before. So what is the competitor you fear the most? And would you go with each other with a drink, or are you too much competitors? I don't know. Who wants to start? Otherwise, I'm calling someone.
University of Science and Technology, China. They are very, very competitive. Specifically, we feel with our lab, whatever we publish, we see echoes within months. They're very good. They've spun up an amazing lab very quickly. It will be very interesting to watch what they can do over coming years.
So no afraid of anyone?
I think Austin just spelled out. We're all probably, I'm in agreement there. I think the biggest fear is the groups that, are operating maybe under the radar, right? You don't see open publication, and then one day, poof, the experiment's been reproduced. It's outperforming the original experiment, right, et cetera. So I think, to Austin's point, that's what has been seen coming out of China in recent years, and I think that will continue.
As someone from let's stay with that, and we're also reaching the end of our panel already. Nevertheless, I would not like to conclude this panel without any final words from your end, and can be anything, just what particular outlook, what kind of particular milestone do you expect in the future, anything, any final words for this panel you think about the topic. And Austin, if you don't mind, maybe we can start with you.
Sure. So I'd just like to reiterate that quantum is looking for people attracted to hard. Certainly in my studies, I studied physics and math and computer engineering, computer science. And I always was interested in having a very broad base of knowledge. And it's what is needed, broad expertise and willingness to say, no, what are the hardest problems in the lab? That's what I want to be working on. So if that describes you, there are many careers waiting for you in quantum. Just do the study. We'll be here when you're ready.
Terrific. Leon, any final words for this panel from your end?
No, just to add on what Austin just said, right? So yes, get on board. I mean, this is likely the decade where quantum advantage will be realized, correct? Where certain science, certain business applications will be solved that cannot be solved right now. And so joining this field, I think you have, it's all about probability and statistics, right? But I would put the odds pretty high that there's a high probability that you have a pretty good chance of being part of some major successes here before this decade rolls around. Lucky 2021, so join us for the ride.
Terrific. And Krista, any final words from your end to the audience?
Yeah, I think, we're really entering an era where we have, it's an opportunity for a quantum computational era, right? It's not just the era of quantum mechanics. This is the era of when quantum mechanics starts to enable us to be predictive, right? Where we can bring that to the computational level. That is a new capability. And if you want to be a part of that capability, right, there are very few decades in which you can say, I was able to enter the field at that moment in time, right, and be a part of that journey. So I agree with Leon and Austin, right? Now is the time to think about working in this space, to be a part of it's in its early stages. You can be part of the development and part of that revolution. I think that's super exciting. And in addition to being this, to this being an exciting and hard area, I would add, if you love learning, right? Talk about a field where you learn all day, every day, right? We are learning how to develop the system. We are learning how to program the system. We are learning how the materials work. We are learning the applications, right? It is constant learning, which, and filled with challenges, and I can't think of something more exciting to work on.
What a great way to end this panel. Obviously, in this panel in the past, I don't know, 1 hour and 20 minutes, of course, we only scratched a little bit the surface. We weren't able to dig very deep into that, but I hope you got a little bit inspired and excited to work in this field. And with you, I obviously mean our audience here right now. I would like to thank you very much, Krista, Austin, Leon, for taking the time and for your inspiring words. And I hope with this brief panel here, we were able to encourage people getting more involved into this topic. As said, it's part of a revolution. It's sort of something completely new. And yeah, thanks a lot for all your time and for the inspiring words and for all the discussions. So, and with this, I would like to close the session and the panel, and hope to see you all soon and healthy again in the near future. Take care. Bye-bye.
Thank you.
Bye. Thank you.